All right, example 3. We are going to continue to find the inverse, but also look at what the graphs of these things would look like and look at the relationship between the graphs of a function and its inverse. So example 3 says we have f of x equals x squared, and it says to find the inverse. Find the inverse of f of x. There's two parts to this. And then we're going to graph both of these. So the first thing that I'm going to do here, right, let's just focus on finding the inverse of x squared. Well, x squared is pretty simple. There's only one operation there, so you could just think, oh, it's just the square root of x. But just to review that, that process of finding an inverse, I guess I'll do it the long way, right? If it's f of x, I would switch this to y equals x squared. I would then switch the x and the y. Remember, this idea of inverses is that you take the inputs and the outputs and you simply change them. You switch them. So I make this x equals y squared. You switch them. Switch. And then you can solve for y. So now I take the square root of both sides. Square root. And this is equal to now y equals, technically now this is plus or minus, right, the square root of x. And so there's my inverse. Now since I started with f of x, and then I changed that to a y, I'm now going to convert this back, this y right here, I'm going to convert back into function notation. So I'm going to say f inverse of x. The inverse is equal to plus or minus the square root of x. And what I'll show you with the graph here is that that this is not plus or minus x, but this is actually just plus. We're going to ignore the minus here, and the reason is because we're saying that this right here, this domain of the original function is all positive number, greater than or equal to 0. So 0 along with all the positive numbers is part of the domain. So you'll see, I'll explain that in the graph, but this is not going to be plus or minus. It's just going to be the square root of x, and really just the positive version of it, not the negative version of it. So here's my inverse. That's step number 1. We know how to find that inverse. Okay, the next step here is I'm going to graph. I'm going to go ahead and graph f, right? So we know how to graph a quadratic equation here. We have f of x equals x squared. I'm going to go ahead and do this really the old-fashioned way. I'm just going to make a table of values where I have my inputs and I have my outputs, in this case, f of x. And if I go ahead and plug in some values here, let's say we plug in 0, well then I'm going to get 0. If I plug in 1, again this is into f, I would get 1. If I plug in 2, I get 4, 2 squared. If I plug in 3, I'd get 9. So this is what f is, and if I'm going to graph that, I can simply take those points and go ahead and plot them. So 0, 0, here's 1, 1, 2, 4, 3, 9. So I have this graph like this, and this looks like my parabola. Now you might recall that parabolas are symmetrical too. And so you might go ahead and say, well then this has to exist too, right? This one, and this one. And I'm going to have a parabola there. Well, that's not the case, right? If we go back to, this is the domain. This is the domain of this original function. So we're basically giving this original function some extra information and putting some restriction on this parabola. And what we're saying here is, yeah, normally the parabola would look like this because you just plug in any number and you get this shape. But in this specific case, we're only going to plug in values that are non-negative, which means I'm not going to plug in anything that's negative. This whole left-hand side of the parabola doesn't exist, And that's why the graph is simply going to look like this, right? Because I'm restricting that domain. So that's what f of x looks like. Now, what does f inverse look like? Well, there's two ways to kind of think about that. One way is just to look at the inverse that I already have right here, right? And just make another table of values, which I can do. So I'll do that over here. I'm going to make another table of values. This time I'm going to have x and then the inverse, f inverse of x. Now, because we know that these two things are inverses, okay, we don't actually have to plug in values and do the whole evaluation over again, because inverses switch the x and the y. The inputs and the outputs of inverse functions are simply switched. So what I mean by that is, in my original function, I plugged in 0, 1, 2, 3. Well, and then I got 0, 1, 4, 9. What I could do is basically take those and put those as my inputs now, because since they're inverses, I know that these x's that I took from the first one would be my outputs. So again, look at the difference between these two functions, or these two tables. Here's f, and here's f inverse. The x's and the y's are simply switched around. And it should also make sense by looking at what the equation actually is. It's just the square root of x, right? So if I plug in 1, the square root of 1 is 1. If I plug in 4, root 4 is 2, etc. But you should always make note of this relationship, in that the inputs and outputs are switched when we have inverses. Okay, and that's just an important distinction to make. So when if we're going to graph this, I can just do the same thing. I'm going to plug in, 0, 0, 1, 1 is right here, 4, 2, and 9, 3. So I'm going to go ahead and graph it, and I get that, like that. So my the graph of this function is right here in blue. The inverse is like this. Now, taking this one step further, you might be wondering, why in the world am I even doing this domain thing right here? Why am I restricting the domain for this original function? Like, what was the purpose of that? So here's the reason, most likely why we restricted that domain. If we didn't restrict the domain, that means that we would have had this parabola go like this. And therefore, the inverse would have went like this. Now, if we did that, the blue graph, or f, would have been a function, because it passes the vertical line test. That means every input has exactly one output. However, its inverse would not be a function, because it fails the vertical line test. Watch what happens here. It fails the vertical line test everywhere. That means that for every input, you have more than one output, and it's not a function. And so just remember, in math, we're always trying to, or most of the time, we're trying to keep things in terms of functions. So that's the reason why we restricted this domain early on, because if we didn't, that means that f inverse, while it would be an inverse, the way that we kind of just showed, it wouldn't be a actual function. So there's your answer to this. Now, the other thing that you're going to note when you have inverses and when you look at their graphs is there is a special relationship between the two things, just visually. If you look at the blue and the green graphs, there really is some symmetry here. There is a mirror image, and the mirror image is is a reflection over this line right here. I'm going to put it like this. This line right here, which is not part of my F inverse graph, but this line right here is y equals x. That's the y equals x line. And you're always going to have this relationship here between functions and their inverses, is that you have mirror images between this y equals x line. So you can see that, for example, this point right here on the blue graph, that's a mirror image if I went right to this point right here. So this point relates to this point over here because the x's and the y's are simply switched. And so you have that mirror image effect. In the same way, this point right here is a mirror image amongst that line right there, there and there, and so forth. And you can see that 1, 1 is also a mirror image, but since it's on the line, it just stays as that point. So that is another very major thing that you want to take note of when you're looking at inverses and their graphs, is that you're going to have this reflection line like this. So to reinforce that point, let's look at Desmos here. And I'm going to put in several functions so we can, again, reinforce that idea or what that visual looks like. So let's just do the one we just did, right? So if I say f of x equals x squared, there's what my graph looks like. Now notice we didn't restrict this domain yet, but now let's put in f inverse of x. Let's not do that actually. I forget how to do function notation here on Desmos. So let's change this back to a y equals x squared. And then if I do the inverse, I'll just do it a simple way, and I'll just switch the x and the y. So I'm going to do x equals y squared. So again, you can see that the red one is a function, the green one is the inverse, and there is a reflection here amongst this y equals x line. These two things are reflected here. Okay, so let's just try another function. What if we did, let's try y equals 2x plus 3. There's y equals 2x plus 3. And if we're going to graph the inverse, remember it's going to be a reflection over this purple line right here. So you should almost be able to just look at this right now and kind of visualize where the inverse would be graphed without even trying to think about what the inverse is. What does a graph look like? It's going to be a mirror image amongst this purple line. So if you were to test it, here I'm just going to switch the x and the y. X equals 2y plus 3. And notice that we get the exact same thing again. We have this reflection over the y equals x line from these two inverses. All right, so let's try one more. Let's try a graph. Let's try an exponential, which we'll get into in chapter 7, and we kind of talked about it already. But let's try y equals 2 raised to the x. There's a y equals 2 raised to the x. It's this exponential growth that we're having here. So nonlinear. And again, if you look at this, and I have my reflection line on here again, I want you to think about, well, what does the inverse have to look like? If I just took a screenshot of this, I gave it to you on paper, you printed it off, and I said, without even looking at the equations, just sketch out the inverse, you should be able to do that, because these are going to be reflections over this line. So think about what that looks like, and let's go ahead and check it, because I'm just going to switch the x and the y. So I'm going to say x equals 2 raised to the y. Turn that on, and look at what the inverse is right here. It's a reflection of that graph. Same thing, let's see what other functions we can put in here. Let's say sine of x, right? We get into trigonometry, right? And here's what sine looks like. It's a wave. Well, what does the inverse look like? X equals sine of y. Looks like that. It really doesn't matter what the shape is or what the graph looks like at all. The inverse is always just going to be a flipped over version of the original graph. Another way to think about this, if you're more of a hands-on, is if you have a graph like this and this was on your paper and you were to crease that y equals x line, you were to just like fold it over that line, then the graph that you originally drew would go right on top of where the inverse is going. It'd be that reflection. Okay. All right, so to finish this up, I want you to go ahead and practice one of these. This practice problem says to graph each function and its inverse using a table of values for each, and then determine the inverse equation and also verify the equations are inverses using composition. So this is really kind of everything that we've learned here in one, so it's a good kind of self-check to see if you know what you're doing here. So first things first, you're going to graph each function using a table of values first. So I'm going to take this, and here's f. So I'm going to make a table of values and go ahead and plot this. So I'm going to plug in 0, and I'm going to get -6. If I plug in 1, I get -5. If I plug in 2, I get -1. Actually, sorry, not -1. I get -2. If I plug in 3, it'd be 9 minus 6 is 3. And so I'm going to start to plot these points that I'm getting from f. 0 is -6. 1 is -5. And then -2. And then 3 goes to 3. Now also note that there's really no domain specification here. So if I'm graphing x squared minus 6, there's that symmetry. There's that other side of things that's the other side of the parabola. So this point's gonna exist, this point is gonna exist, and so is this. So what I'll say there is -5 is also gonna be, -1, -2, and -3. Those are all also gonna exist there in my graph. So here's my graph. Kind of a bad graph. But then it says go ahead and graph the inverse. Well, without even finding the inverse yet, we should be able to graph this pretty easily. And we'll actually find the inverse in a little bit. But the graph shouldn't be hard because remember, I'm going to just interchange the x's and the y's. So I know that here's what I'm going to do. Actually, I'm going to switch this. I'm not going to put these next to each other. I'm just going to say -1 also goes to -5, 2, -2 also goes to -2, and -3 also goes to 3. So I can erase these. So basically, because I know that if I'm going to graph the inverses, the x's and y's are just switched, I can really just take my y's for the first one and put them as my x's, and my x's from the first one and put them as my y's. And the graph is going to show that, kind of like what we just saw in Desmos, but -6 would go to 0. That means I'm right here. -5 would go to 1, but -5 would also go to -1 as well. You can see this one, but also this one here. -2 goes to 2. It's right here. And -2. So that goes, it's shared with this point right there. And then 3 goes to 3. Let's see, 3 goes to 3, that's right here. But 3 goes to -3 as well, that's right here. So the inverse is going to look like this. So I have the function, which is in blue, and then I have the inverse, which is in green. Now I'll also say now that the inverse of this function is not a function. F is a function, but f inverse is not a function because you can see that this green graph does not pass the vertical line test. In other words, we have inputs going to two different outputs right there. That fails the function test. So just take note of that. Now, the next part of this is to determine the inverse equation. So that was another thing that we did. How do we find the inverse of this? Well, let's find the inverse. I'm going to change this to y equals x squared minus 6. Then I'm going to switch the x and y. Right? The x's and y's are just swapped. And now I'm going to solve for y. So I'm going to add 6 to the other side, plus 6. So y squared equals x plus 6. Then I'm going to take a square root of both sides. So I'm going to have plus or minus the square root of x plus 6 equals y. And since I started in function notation here, f of x, I'm going to write this as f inverse of x equals plus or minus the square root of x plus 6. And since everything is in green for that one, I'm going to put that in green, and there's my inverse equation. Okay, and then it says to determine the inverse equation, or so we figured out the equation, and then to verify the equations are inverses using composition. Okay, so we talked about that as well. So I'm going to now prove that these two things are indeed inverses. Of course, we know they are. We just did the inverse right here, and we're showing it on the graph. Clearly, they're inverses. But let's review what function composition tells us. If we want to prove it, we would have to take f of g of x, and we would have to show that that equals x. So f of g of x here would be f of and g of x. In this case, let's switch this from g of x to f inverse of x, because that's the notation that we're using. It's not g. The inverse of x is root x plus 6. So, and I realize it's plus or minus. So we could do both of those. We could first do the plus version of it, and then we could do the minus version of it. But you'll see what happens here. So I'm just going to put plus or minus, because we can do both. X plus 6. So what happens when I take root x plus 6 and I plug it into x squared minus 6? So if I put in either a plus or a minus, okay, I could do those separately, but it doesn't matter. It doesn't matter if it's plus or minus, because if you square this square root, if you take the square root of x plus 6 multiplied by the square root of x plus 6, you'll just get x plus 6. So this is going to become x plus 6, and then I'm going to bring down this minus 6, and lo and behold, we just get an x. So my final statement here is f of f inverse of x. If I do this composition, then it comes out correctly. I start with x and I end with x. Now, if we were really doing this properly, then we would have to do it the other way as well. So what if I did f inverse of f of x? What if I do the function composition the other way? I just plug in, or I do substitution the other way. Well, that would look like this. F inverse of, and the original function is x squared minus 6. So I would be plugging in x squared minus 6 here. And here now I have plus or minus the square root of x plus 6. But instead of x, I have an x squared minus 6. So I'm going to take this x squared minus 6 right there and plug it in. And remember, the original function, again, was where was it? Oh yeah, it's right there. Plus, so this would be plus 6 right here. Right? So, so I'd have plus or minus the square root of x squared minus 6 plus 6. I really can just cancel off those 6's, and then I'll have x squared. I know that the square root of x is, the square root of x squared is going to be just x, or actually plus or minus x. So it gets a little confusing here, because if this is already plus or minus, and then this root x squared can be plus or minus. I'm not going to go into super details here. This whole thing, we're just going to say goes down to x. The square root of x squared comes back down to x. That those plus or minuses basically will cancel off each other. And that is how we're going to demonstrate that if I start with x, I'm also ending with x this way. So either way I do it, I'm going to get x both ways. And that is the whole problem. So we're graphing it. You can understand how the graphs work, the table of values, how you can interchange the x's and y's and get the other graphs. Also, how we can find the inverses mechanically just by switching the x and y and doing the algebra on it. And then also using the idea of function composition to show or test or just verify that these two things are indeed functions. Now, notice too that the last thing I'll say here is that the blue function, the blue graph, is a function. But notice that its inverse is not a function because it doesn't pass the vertical line test. So just in that first example, if we wanted our inverse to also be a function, we would have to restrict the domain and basically for this blue function say, all right, I'm not going to graph, let's say, one of these halves. Let's just say this one right here, because that means that this part of the green function would also not be graphed as well. And so then I would have a function and I wouldn't have that discrepancy in terms of functions. But we can still do it this way. Just make sure you understand what is a function and what's not a function.